So now that we've talked about boosting and we've talked about decision trees in this course, let's put those concepts together and talk about XGBoost, which is arguably the most powerful machine learning algorithm out there today. So, very important chapter here. XGBoost stands for Extreme Gradient Boosted Trees. Now remember, boosting is an ensemble method. The idea is that we take a model and we have multiple versions of that model chained together. So what happens is every tree within our boosting scheme here is going to boost the attributes that led to misclassifications from the previous tree. So basically, we have multiple trees that are just building on top of each other to correct the errors of the previous tree before it. And it turns out this rather simple idea is really, really amazing. XGBoost is routinely winning Kaggle competitions. It's very easy to use. It's very computationally efficient. So it makes for a really good choice for an algorithm to start from. Whatever your problem, whether it's classification or regression, there's a really good chance that XGBoost is going to prove to be the best algorithm to actually try to make a model for your data and make accurate predictions based on that model. And it's really easy to use. I mean, it's almost disturbing how easy it is. Under the hood, it has a lot of really cool features that make it so good. It uses something called regularized boosting. So this is what sets it apart from other boosted tree methods out there. Regularization is something that prevents overfitting, so it ensures that the model we end up with is generalized and it's not really overfitted to the set of data that you trained it on. We'll talk about regularization in more detail later in the course, but under the hood it uses L1 and L2 regularization, which again we'll talk about more later. Another really cool feature is that XGBoost can handle missing values automatically. So it will automatically figure out the best way to handle the missing values in your data. You don't have to think about it too much. That's a really cool feature because, dealing with missing values and imputing those missing values can be a huge part of your job as a data scientist, but XGBoost just kind of makes it happen. It also can be run in parallel. So that's the key to its efficiency. It can actually take advantage of all the cores on your CPU, or even take advantage of a cluster of computers. It can be run in parallel across multiple threads, and this also means that you can use it for big data, for large data sets that won't necessarily fit on one machine. So not only is XGBoost a really powerful and accurate algorithm for small data sets, it also scales well. So what's not to love about it, right? Another nice feature is that you can do cross-validation at each iteration. We haven't talked about cross-validation too much yet, but the idea is that you can evaluate the performance of this algorithm of XGBoost at each step of its training. And that allows you to do things like say, well, I'm not really seeing much more benefit from further iteration, so I'm going to go ahead and stop this iteration early. Or I can actually find the optimal number of iterations as I'm training it. So like I can monitor the accuracy of my model as it iterates and figure out when I should stop it and find that optimal point pretty easily. It also supports incremental training. What I mean by that is that you can actually stop the training of an XGBoost model and then save it and come back and pick it up later again. So if you want to actually split up the training over a period of time or across multiple batch jobs, that's a possibility as well with XGBoost. Also, it allows you to plug in your own optimization objectives. This makes it very flexible in nature. So whatever the problem you have, if you can describe it in terms of something that you want to optimize, you can probably get XGBoost to work on it. And finally, it uses a feature called tree pruning. So unlike normal decision trees where it just stops branching once it stops seeing a benefit of doing so, it kind of takes a different approach here. We'll actually go very deep by default and then try to prune that tree backwards. So that generally results in deeper trees but more highly optimized trees, and that's part of the key to its success. Using XGBoost is ridiculously easy. To install it, just type pip install XGBoost from your Anaconda prompt, and once it's installed, you can just start using it. It also offers interfaces on the command line interface for C++, which is what it's written in natively, also for the R language, Julia, and it has a JVM interface, so you can use XGBoost very efficiently within programs like Java or Scala, and Spark using Scala, for example. So it's not just made for scikit-learn and Python notebooks. It's more general than that. And as such, it has its own interface, so it's not really made specifically for scikit-learn. So things are a little bit different when you're using XGBoost within scikit-learn within a notebook. The main difference is that it uses something called a D matrix data structure to hold the feature and label data, but using it's very easy, and there's a very easy way to create one of those D matrix structures from a NumPy array. So in practice, it's not a big deal. And you'll pass in all the parameters for XGBoost as a giant dictionary. We'll talk about that in a second. Once you've done that, all you have to do is call train on the model and then call predict on the trained model to make predictions from it. It's really, really easy. What the hard part is tuning all those hyperparameters of XGBoost. So there's a bunch of knobs and dials on XGBoost, and to get the best results, you need to choose the right settings, and often that's just done through experimentation. Some things are going to be pretty straightforward. For example, you can choose your booster. You'll probably want to use a tree for classification problems or linear for regression problems. And you also need to choose your type of objective function. So for example, I might choose softmax if I want to just choose one of many classifications and choose the best classification for any given thing. Or I could say I want multi-soft-prob. That gives me actual probabilities for each classification. So that could potentially allow me to get a list of likely classifications, more than one, for each thing that I'm trying to predict. Beyond that, the rest need to be learned through experimentation. So eta is probably the primary parameter, the biggest knob that you have in XGBoost, if you will. You can think of that as the learning rate. So it's going to adjust the weights on each step of training. And the default value of that is going to be 0.3, and often you'll find that in practice, lowering that a little bit, to 0.2 or even lower will often produce better results. So that's the main thing you want to start tinkering with once you're trying to tune the performance of your XGBoost model. Some other important parameters are max depth. That's going to be the maximum depth of the tree. And obviously, if that's too small, you're not going to be able to create a very accurate model. But if it's too large, you might end up overfitting. So tuning that can be a very important thing to try to get right. There's also one called min child weight. This can also be used to control overfitting, making sure that your model is not too specific to the data that you trained it on. But if you set it too high, you'll end up underfitting. So, you need to get the right balance on that as well. There's a large number of other parameters on XGBoost as well, but these are the main ones that you want to fiddle with and experiment with. And again, sometimes you just need to experiment to figure out which combination of values works the best. Within a Python notebook, you can use tools such as grid search CV to automatically try an array of different values for these parameters and automatically find out which one is the right one. Or if you're using a larger system like AWS SageMaker, it will have things like automatic hyperparameter tuning jobs that you can set up to try to find just the right combination of parameters here. So tuning these just right are key to getting the best performance out of XGBoost. But as you'll see, you don't have to really think too hard to get good results out of it. So remember, XGBoost is almost all that you need to know for machine learning these days in practical terms. For simple classification or regression problems, odds are you're going to get the best results from XGBoost, and using it's really easy. So with that, let's actually see it in action. We're going to throw it at the iris dataset. This is a common dataset used for educational purposes. It's just a dataset of a bunch of flowers, and they measure the length and width of both the petals and the sepals. The sepals is just a specific kind of petal. I think it's the one on the bottom of the iris flower. And based on those measurements of the petals, we're going to try to predict what subspecies of iris that flower actually belongs to. And as we'll see, XGBoost is extremely good at this. So let's dive in and give it a shot. So let's play with XGBoost. We'll start by bringing up our Anaconda prompt as always. So go to my start menu here and go to Anaconda prompt, or on Mac or Linux, bring up your terminal. First thing we need to do is cd into where our course materials are stored. For me, that's going to be cdc:\ml course. And before we spark up the Jupyter Notebook, we need to first install XGBoost itself. So I've already done that, but you probably haven't. So go ahead and type in pip install XGBoost to take care of that. For me, it won't do anything because I've already installed it, but for you, it should be going out there and downloading and installing the latest version of XGBoost. Once that's done, we can type in Jupyter Notebook, Jupyter with a Y. Once we're in here, go ahead and find the XGBoost notebook and open that up. And let's get started. So again, using XGBoost is really easy. There's not a whole lot here to look at because there's not a whole lot to do. It's really easy to use and it just works. So we already installed it, but as a reminder, that's how you would install it if you didn't already. And again, we're going to be experimenting with the iris dataset. The idea of this is that we have a dataset of flowers where we have measurements of both the petals and sepals, which is just a special kind of petal, the length and width of each. So for every flower, we're going to have 4 measurements, 4 attributes or features, if you will, the length and width of the petals and the length and width of the sepals. And what we need to do is predict which subspecies of flower it is based on those measurements. And it turns out there are 3 subspecies of iris flowers, Setosa, Versicolor, and Virginica. So let's go ahead and load that data up. Fortunately, that's already built into scikit-learn, so we just have to say load_iris to load that up. And we can explore the parameters and features of that data here. So we'll do data.shape to figure out what's in it exactly. To try to understand what's in there, go ahead and hit Shift-Enter in there to actually run that. And we can see that this consists of 150 samples, so there's only 150 flowers in our data set here. Every flower has 4 features, the length and width of the petal and the length and width of the sepal. And the possible target names, the actual categories that we're trying to predict, the labels, are setosa, versicolor, and virginica. So let's get started by dividing up that data into both a training data set and a test data set. The idea here is that we want to make sure that we're only training our model based on our training data, and then we're going to set aside 20% of our data to actually evaluate the model with. So we want to make sure that we're holding this test data set aside and not training the data on it so that we can say, okay, model, okay, XGBoost model, how well do you do on predicting subspecies for flowers you've never seen before? So this makes sure that we're not training on the answers. We're not like cheating, if you will, right? So the idea is that we're going to set aside 20% of our data for testing purposes, train the model on the remaining 80%, and then evaluate the model based on that data that was withheld. So that's what train test split is doing. It's just randomly splitting up that data that way. So we pass in the actual feature data, the label data, and we say that we want to reserve 20% of the data for testing. And we can give it a specific random state to make sure that we get the same results every time we run this. Now we'll go into a bunch of different arrays here. X is basically by convention the feature data, in this case the lengths and widths of the petals and sepals, and Y by convention refers to the label data. So that's going to be what subspecies it is. So what this means is that the feature data, the actual measurements of the petals, is going to go into XTrain for the training data set and XTest for the test data set. And the labels, the answers, if you will, of what subspecies it is, will go into Y_train for the training data and Y_test for the test data. Let's go ahead and run that before we forget. And now we can load up XGBoost itself. So as we said, XGBoost is a little bit quirky in that you have to use these D matrix things instead of just using straight up NumPy arrays. But as you can see here, it's really easy to create them from a NumPy array. So we're going to say the entire training data is going to be a D matrix that consists of the training feature data, the actual measurements, and the label data, the actual subspecies. And we do the same thing for the test data. So we basically embodied all of the features and label data for both training and testing in these two D matrix objects. Go ahead and Shift Enter to run that. Next, we need to define our hyperparameter values. And as we said, this is often the hardest part of the whole thing, just trying to find the right values of these settings, if you will. And so we'll just start with a guess. So let's say that we're going to start with a maximum depth of our trees of 4. Eta, we'll start with a default learning rate of 0.3. And again, usually you want to go a little bit lower on that, if anything. Our objective function will be softmax. Softmax just means that we want to look at the most likely classification for each flower. So in contrast, we could use softprob to get the actual probabilities associated with each individual subspecies. But I'm just interested in one answer per flower. So I want it to automatically pick the best classification value. And that's what softmax does. It picks the classification with the maximum probability. And we will specify the number of classifications that we have, in this case 3, because there are only 3 subspecies to choose from. The other thing we have to guess at here and tune is the number of epochs or iterations, if you will, call it what you want. Basically, how many times are we going to actually run this algorithm over? So with that, Shift Enter, and we can then train our model with one line of code. It's just that easy. So by saying xgboost.train, we just pass in that dictionary of parameters, the actual training data, that's that D matrix object, and how many epochs we want to run it over. Go ahead and Shift Enter, and you can see it's already done. Like we said, XGBoost is really, really fast. So now we can just make predictions based on that trained model. So let's go ahead and call predict, passing in that test data that we withheld, right? So remember, we took 20% of our data set, set it aside so that the model never saw it while training, and now we're going to evaluate how well it predicts flowers that it's never seen before. And if we print out those predictions, we can see that it's printing out the category numbers of each individual flower in that test data set. So I forget what these actually correspond to. I think 2 means virginica, for example, right? So these are the actual subspecies predictions for each data point in the test data that the model never saw before. Let's see how well it actually did. So I'm just going to call accuracy_score from the scikit-learn metrics package there. And I'll pass in the actual known correct values, which are going to be in Y_test. Those are the correct classifications that we know, and the predicted values, and we'll compare how well they actually match up. And look at that. It's actually perfect. You do not see that very often. I mean, we just guessed at the right hyperparameters for XGBoost, and even just guessing, we got perfect results out of it. I mean, obviously those are exceptional. You're usually not going to get 100% accuracy, but wow, that is amazing performance here. Now, normally as a hands-on activity, I'd have you try to improve the accuracy by messing with the hyperparameters further, but you can't improve on 100%. So instead, what I want you to do is try to make this model more efficient. Could I actually get away with fewer epochs or iterations? Could I actually get away with smaller trees by lowering the max depth parameter? So try to optimize the simplicity of this model and therefore its performance and see how simple you can make it before actually losing accuracy. So play around with that and get a feel as to how those hyperparameters affect the actual accuracy of your result. But yeah, that's XGBoost in action. As you can see, it produces awesome results. It's not hard to use. It should be your go-to algorithm in a lot of cases.